Okay, this is the first of 4 videos on the Earth unit. This will be the Earth's atmosphere unit. I'm sorry, video. So part 1 of all 4, you'll need to watch all of them or just check out the notes and read through the book. You don't have to watch the videos, but we'll do this as part of the flipped classroom approach, where instruction will take place outside the classroom and activities will take place in the classroom. It just sounds exciting, doesn't it? Structure of Earth. We're not really going to get into the interior and what it's all about. I really like this image because it just really kind of shows how small that atmosphere is. Very thin, about 60 miles. If you could get a car and turn it vertically and drive, it'd take you about an hour to be into space, right? That's not very thick compared to the entire size of the entire size of the Earth. It's fairly small. This is the Earth's atmospheric composition, more or less, at the current moment. The mass of the atmosphere is very, very, very small, right? 0.1% of the mass of the entire planet. It's gas, obviously. I mean, it does have mass, but it's very low density, of course. Of these gases, 78% of all of air, as you would know it, is nitrogen. 21% of it is oxygen, which we need, obviously, for cellular respiration. And 1% is argon, about 1%. And then everything else is less than 1%, including carbon dioxide and other things. So, air is a homogeneous mixture, or homogeneous mixture, however you want to call it. Things are not chemically combined, they just happen to be mixed very well. Early Earth's atmosphere was a lot more CO2 and less O2. In fact, it was fairly hospitable for living organisms of any kind, except for cyanobacteria or blue-green algae. Blue-green algae is believed to have developed somewhere around 3 billion years ago. And slowly but surely, cyanobacteria, which is basically a bacteria that can photosynthesize, started intaking CO2, which is quite abundant in the old atmosphere, and as a byproduct released O2. Well, this took a long time to change this atmospheric composition. It's probably changed it by about 20%. Okay, let's move on past this. It's a good little question. You might want to check that out. Abundance of gases. See if you know that one for the old test. Okay, so the atmosphere is broken into different layers. And these layers are divided based on temperatures. You can see the large swings in temperature. This is what divides that. We live in the troposphere, which is the densest part of the atmosphere. As you go on up, it becomes less and less dense. This is where most of the Earth's gases are. It is typically referred to as the weather zone. All weather occurs in this layer, right? Because the clouds don't really condense above the troposphere. Second layer up is called the stratosphere. It is where planes typically fly, and it depends on the flight, obviously. If it's a short flight, they won't go all the way up to the stratosphere. But for longer flights, they definitely will go into the stratosphere because you go above the clouds. And that is a lot more comfortable flying. And also, because the air is less dense, they're able to go faster in the stratosphere with less fuel. So, stratosphere also contains the ozone layer. And ozone layer is a thick layer of O3 that blocks ultraviolet light from penetrating into the planet, right? Now, not all ultraviolet light, of course, but roughly 99% of it. Above this is the mesosphere. Meteors, as they come into the planet and don't make it quite into the planet, typically burn up in the mesosphere, create meteor showers. So, it is meso means middle, so that's where we get the word mesosphere, kind of in the middle. The upper one is known as the ionosphere. So you'll oftentimes see another word, troposphere. I'm not troposphere, sorry, exosphere. But the space station is in the ionosphere, right? This is basically what most people think of as space, right? The space station kind of orbits here. This is where the um, space shuttle used to go and orbit around, right? And it's basically the upper regions of the atmosphere, but it just doesn't have enough air to, sustain life, obviously. But also, the gravity is super weak here from being far away from the planet. So the ionosphere blocks radio waves. So, and that's kind of a unique thing. Sometimes radio waves can bounce off the ionosphere and kind of reflect off. So it's an interesting layer in that regard. Might be something you want to do. Sort those. You do need to know the layers and in what order. I mentioned ozone a minute ago. It is 3 oxygens bonded together covalently. These 3 oxygen molecules, when bonded, will disrupt UV light from coming into the planet. There was a problem in the 70s and the 80s, really the 80s. And the problem is that there's a hole in the ozone layer starting to open up, especially over Antarctica. And we're kind of confused about why that was, and then we connected it to the fact that in the 70s, scientists developed this artificial propellant called chlorofluorocarbons, and are oftentimes referred to as CFCs. Chlorofluorocarbons were used as a propellant in hairspray and any other kind of aerosol kind of, spray. I don't know what you call them, but anyway, the CFCs were disrupting the O3 in the fact that it was breaking up the molecule into O2 and a free oxygen. And while not dangerous, it just wasn't doing its job of blocking the UV light. So we stopped using that in the 80s. Most people in the world have stopped using it. Countries made bans on it. And the hole in the ozone layer is slowly healing itself. It is already better than it was. So we're talking about surface heating, how the planet heats up. So the planet heats up by infrared light. And infrared light is a spectrum of the light that the sun produces in large amounts. And it is the only spectrum of light that actually produces heat as we know it and heats up the planet, right? So it's the most critical type of light from the sun, really. Obviously, visible light is important for us too, but infrared is definitely critical. So when this radiation comes in to the planet, it is either reflected or absorbed. And the reflection and absorption of something is dependent on that object's albedo. So albedo is what's known as the reflectivity of a surface. So if you look here, the cloud has what's called a high albedo, so it will reflect easily, right? The darker colored surface here will not reflect as much, so it will therefore absorb more of the heat energy. A good example of this would be a road, like a blacktop asphalt road. It gets very hot because it's a darker color and will absorb in a lot of infrared radiation. So this energy will get re-radiated out, and this is a critical part that you really need to understand. This energy will get re-radiated out, and the atmosphere actually absorbs energy from the re-radiated energy. So it's like a skillet or something that gets really hot when you're cooking on it. When you turn it off, the skillet stays hot for a long time, and it re-radiates that energy back out into the air around you, right? So the molecules of atmosphere actually only, well, I hate to say only, but mainly get warmed in this way, because this is a slow release, right? So this is penetrating fast. This will soak in, and then it slowly releases up here, and the air molecules warm up from this, more so than the incoming light. So things that have high albedos are snow, clouds, any kind of shiny surface, right? Ice. So white, any kind of like lighter color things. There's a reason you should wear like a lighter color clothes in the summer, because it doesn't absorb as much heat and it reflects a lot more. And it's oftentimes the reason summer clothes are lighter colors, right? So Inversely, you have things that have low albedos like dirt, right? Asphalt, trees. These are darker things, right? And here you see the shirt is black. This has a low albedo. And this is the reason that most coats are darker colors, winter coats. No, not all, but I say most. Like especially like a big trench coat or something like that. It's a darker color because it will absorb more infrared energy into you, right? And it will keep you warmer. Not just because it's a thick insulator, but because that energy, the infrared energy, will absorb more into you. So. It's a good little question. You might want to answer that on your own there. Last thing, well, not last thing. I was thinking back. We got another couple things to talk about, but let's talk about greenhouse effect and global warming. So, the greenhouse effect is and global warming are things that are oftentimes mixed together, and obviously they do go together, but they're not well understood by most people. Right? The greenhouse effect is the idea that heat that gets radiated into the atmosphere stays in, right? Then I have a picture of a greenhouse here. That's how a greenhouse works. Infrared light energy comes in, and it bounces off of the glass. When it keeps bouncing around, and it will slowly release. So what happens is the greenhouse itself stays warmer for longer periods of time without the need of a heater. The atmosphere does the exact same thing, right? Energy will radiate in, and it will kind of bounce around inside the atmosphere, and then eventually it'll go back out and leak out into space, right? Now this is critical, right? Without that kind of bouncing around of that heat energy, right, the atmosphere would be way too cold to sustain life. So we need the greenhouse effect. We obviously don't need too much of the greenhouse gases that retain this heat, because what happens is if you have too much of it, you have what's going on in Venus, which that every day gets a little bit hotter, a little bit hotter. We certainly don't need that going on. We're very glad that a lot of this energy does radiate back out into space eventually, but it's a nice thing to have that kind of trapped in there for a little while. Kind of like a blanket, when you're cold in your bed and you add an extra blanket to it, right? It helps to trap that heat in, right? Your body's what's creating the heat. So the problem with greenhouse gases is not that they're present. The problem that we're having now with the planet is that humans are artificially adding too many additional greenhouse gases that have not been in the atmosphere for billions of years. So a lot of these greenhouse gases are CO2, methane, H2O vapor, right? Water vapor will retain heat. So any of these things that are added artificially by humans, when I say artificially, I mean like not in a natural process, right? We're burning things and adding CO2 and so forth. But as we're adding them, this more and more of the heat energy is getting captured, and what should be released into space. This is slowly heating the temperature of the planet up, right? So, and that's what global warming is. Global warming is not like the planet's going to melt down and this kind of thing, right? The idea of global warming is that with the addition of these greenhouse gases by humans artificially, right, it's at least a slow warming of the planet, and it is slowly heating it up, right? And I mean, don't think that you need to all of a sudden, go out and buy a boat because we're going to be all underwater in the next 10 years. That's not the case. It is a slow process, but it is, in my opinion, this is a highly debatable topic, right? But it is my opinion that it is slowly heating up if you look at data. Last thing we're going to talk about is the origin of Earth's atmosphere, right? So, when the early solar system was forming, right, the nebular theory and all that, gases were collected, right? And so were rocky materials, which is what made up most of our remaining planet, of course. We had large amounts of gas, and larger amounts of gas than we do now. But the planet doesn't have enough gravity to hold on to or retain these lighter gases like hydrogen and helium. And they outgassed into the outer space after about 1 billion years. It probably took roughly 1 billion years. Obviously, the time's a question mark. But this is the reason helium balloons go up. So you can see in the picture from the movie Up, right? And the balloons are bringing the guy's house and this kind of stuff, right? And that's a great film. But this is why helium balloons go up, because the planet doesn't have enough gravity to retain hydrogen and helium. So these things are so light density-wise that they just whoop, go flying up, right? Literally. So that's the reason we don't see these things by themselves on the planet very often, right? Especially helium, or especially hydrogen. But helium is only like kind of found in pockets within the rocks, and they mine it. It's actually very valuable because it's so rare. It's theorized there'll only be like another 150 or 200 years more of helium, natural helium found. So, but who knows? So later atmosphere, like that's kind of proto-atmosphere, if you will. Later atmosphere was outgassed by volcanoes, right? And the planet's a big giant molten mess, right? So volcanoes start spewing all over the planet at all times, and large amounts of CO2 and H2O, right? Which is common now when we see volcano explosions. We see other noxious things like, nitrous oxide and sulfuric dioxide and so forth. Spewed out from volcanoes, but and proto-Earth was very much had a lot of those compounds in them as well. However, those kind of settled down, and because volcanoes weren't exploding, by the gazillions. But it did spit out large amounts of CO2, which is what led the cyanobacteria to start converting that CO2 into O2 once life developed and this kind of thing. But the water vapor is key, right? What the volcanoes really spit out was large amounts of water vapor. And this water vapor condensed into rain, and that rain lasted for thousands of years probably, right? You're talking rain every single day for, hours and hours and hours and hours and hours and hours, because these things are just forming tremendously large clouds, and it's just raining and raining and raining, and who knows for how long it rained. Probably 10,000 years or so, off and on every day or every other day for 10,000 years, right? It's a lot of rain. And as that rain started collecting into lower regions of the earth, which we now know as the oceans, right? As it was hitting the rocks and kind of washing out into rivers, and rivers washing into what is now the ocean, it was picking up lots of salt compounds, right? And these salt compounds from the rocks and minerals of the proto-Earth are what caused the oceans to be salty, right? This is what causes salinity in an ocean. So, all right, well, that's part one, the video the Earth's atmosphere. So stay tuned for part two, Earth's interior.